Here.
Oh, can you? Is it?
Yes.
Perfect.
Okay. Hello everyone. My name is Ivan, and I'm honored to introduce to you our first external speaker, Dr. Joaquim Garcia. He has earned his PhD degree in operations research at PUC Rio, at which time he worked at the very prestigious LAMPS lab. And he's currently core developer of the jump package we've been using for optimization in this class. And also he's the head of R&D at PSR, which is an energy consulting and analytics company, which you'll be familiar with if you work on energy related topics like I do. So that's the introduction for Joaquim, and let us welcome our first external speaker.
Joaquin, you have to share your screen again.
Yes, because of the recording. I didn't notice that. Okay, so you should be able to see my screen right now. Can you see?
Yes.
Can you see the slides moving now?
Yes.
Okay. So thanks for the invitation. It's always a pleasure to present some of these topics. I hope this can be of some help for some of you or most of you. And it's a topic that I think it's very interesting, and I hope it will be for you as well. I think we can keep the conversation interactive. So please feel free to pop in, ask questions while I'm speaking. I'll be happy to respond. And what else? Yeah, and they don't have to be questions. They can be comments related to the other classes that you have been having. I haven't participated, so I might not have the full context, but I think it would be nice for you to discuss, and I can jump in and comment if I can understand a little bit of the topic, and I have correlations that I can make with the topic at hand. So today I want to speak to you about multi-stage stochastic programming, and more specifically also an algorithm for solving multi-stage stochastic programs, which is called stochastic duodynamic programming. So multi-stage stochastic programming, as it has in its name, it has to do with mathematical programming, has to do with uncertainty, and it has to do with time coupling. So solving a bunch of problems that are connected in time. And from what I've seen in the syllabus, this is related to a bunch of subtopics that you guys have been studying over here. So I'll start from the very basics. In some of it, I might go slightly fast. If I do, please stop me. I can come back to it. There's absolutely no issue with that. If I go too slow, you can also tell me that I'm moving slow. I can move faster. Fair enough. So going back to the origins of it, multi-stage stochastic programming is way before this work. Go on. Somebody wanted to say something?
Yeah, me. Can you hear me?
Yes, please.
I'm going to very briefly connect very quickly what we did before, just before you dive into the history of this, if that's okay.
Yeah, please do.
Yeah, so in the previous classes, we looked at how to build the constraints on optimal control problems, right? We learned how to solve optimization problems. And then we had a look into how these optimization problems play a role inside control problems, right? So we looked back into now that we know how to model the physics of this and we know how to solve problems, how can we decide optimally to control a system, right? mathematical programming, maybe we didn't mention with that name, is the same as optimization. That's the equivalent. So he will be presenting this framework inside the optimization field for solving these problems. One thing that we kind of mentioned in the first class, but we didn't go too much into details, is the fact that we were solving deterministic problems. The physics that we were looking into are deterministic things, right? So the constraints were equality constraints that linked the states, the previous states to the next states of your system, and so on, depending on all decisions. There is a very subtle point connecting where we were previously to now in this multi-stage, meaning these control problems that span over time that have stochastic uncertain parameters. And Joaquin will kind of like dive into this. Is this more or less clear why this lecture is where it is, why we're having here? Is anyone like confused at all to like what this lecture will be adding to the lecture? I don't see either positive or negative feedback.
I think it's very related.
Yeah, perfect. All right, Joaquin, thank you very much, and sorry for the interruption.
Okay, no worry. Please keep going with those. I think it's great to relate with what you guys have been doing. Okay, so as I was saying, multi-stage stochastic optimization or multi-stage stochastic programming has a lot to do also with optimal control, like Andrew was saying. So in both cases, you have a dynamic system and you want to figure out what kind of actions you want to take to do something with that system. Usually operate that, keep that stable, make it do some sort of action that you're willing to do, and to do that usually in a cost-effective way, whatever cost means to you, which can be how fast you do something, how much money you spend at something, or whatever. So even multi-stage stochastic optimization is something that, and optimal control, of course, were both things that were done way before the first appearance of this paper in 1991, which is probably a little bit before everyone here was born. But this paper, it was seminal in the sense that it presented this algorithm that I was talking about, which is called SDDP, which is short for Stochastic Dual Dynamic Programming. It's an interesting paper to read. It's not super heavy, but I will go through an explanation of the algorithm, which is not the same as the paper. I would try to use a lot of images so you can grasp some of the ideas and we can go back and forth together. There are some interesting curiosities about when this paper was conceived, how this paper was written, and you can see some of that in the subject to interview of Mario Pereira, which is, you can see here, the first author of this paper. He was also my thesis advisor and my mentor at PSR. There's a link over here, but you can quickly find that on YouTube. There's a lot of fun stories about it. So I'll leave it for later. You guys can have fun about that in your free time. Okay. So now I want to go really quickly through some of the very basics. From what Andrew was saying, you certainly, well, most of you know that very well. Some of you might not know so much, but I like to keep this in the presentation because it helps to put notation in the correct place. And sometimes it makes it easier for some people to feel comfortable about, starting from something that they already know about. So the very basic is linear programming. So here I am writing a general linear program, which has an objective function, a decision variable x, and some constraints, which can be equality constraints and inequality constraints. So nothing special here. Like Andrew was saying, you guys have studied methods to solve that, interior point methods, and other related methods. Newton method can also be used as part of the solution for that when you're doing interior points, and so on. So this is to keep notation and get you guys up and ready with the typography that I'm using, because this small problem will only grow throughout the presentation. And the idea is exactly that. Try to add more and more stuff to this thing until it becomes very complex, but also ready to represent very realistic problems. So throughout this entire presentation, and I try to be careful with that, although I might have failed. X will be one of the decision variables at least, and big letters will represent matrices, and the other ones will represent constants. Whenever I have a decision variable, it typically will be below the minimizing sign over here. Sometimes you see me speaking Portuguese implicitly, which is this SA over here. It should be ST, which is subject to, but in Portuguese it's SA. So sometimes I forgot some of these things. I will get that fixed for you in the next version of the slides. Okay, so linear program can be even more general than that. So I just threw here a slightly more complicated thing in the sense that, yeah, the linear constraints, they can be not only equality, but they can be greater than or smaller than, and the variables can be either free, like x3, or they can be less than 0 or upper than 0. There's even more general versions of that. Nothing special over here, but just saying that, yeah, things can get slightly more sophisticated if you need to. A key concept when you're doing optimization is the concept of duality in linear programming. Sorry again, because some of you already know that, but here is the same linear program that we have been playing before. X is the decision variable, like I was saying. Now I just added this Z star over here, which is the optimal objective solution, optimal objective value. This optimal objective solution would be the X star, and the optimal objective value would be the Z star. And it's interesting that related to every single linear programming problem, there is an associated dual programming problem, which is also a linear programming problem. Like you can see, there's an inequality over here. There's a decision variable here, which is pi at this point. And there's an objective function. There's also linear. And they have this very interesting relation because you can see that the same letters appear in both sides except for x, which is the decision variable here, and pi, which is the decision variable on the other side. But there's the same kind of A matrix over here, B vector and C vector. They both appear in both sides. So you can see sometimes I've seen people relating that to your upside down version of the problem if you're into Stranger Things and other shows like that. But not only this is a linear program by itself, but it contains a very deep relation with the original problem, which we call, well, because we're calling the second one dual, the first one will be called primal. The primal and the dual have this very deep relation between each other, which is every feasible solution of the primal will be greater than or equal to any other possible feasible solution of the dual. So this is what people call weak duality, and there's also strong duality. In strong duality, we are just seeing that, yeah, when you're talking about optimal solutions, both of these numbers will agree. So the Z star will be equals to the D star. But moreover, another interesting point about duality in linear programming is this very interesting point that also relates the dual variables, so the dual decision variables of the decision variables of the dual problem, with something of the primal problem. Z star, again, was the optimal objective function solution. and B is the right-hand side. So if you compute at the solution the derivative related to the B vector over here, you get exactly pi. This will be important further on in this talk. You probably might have seen that or used that in some other algorithms. But this is a key relationship between these two problems that is also extremely important. Of course, you can have some of that in the opposite direction for completeness, but that will not be the explored over here. So before going deeper, I want to motivate why we would be interested in multi-stage stochastic programming. And my favorite kind of problem, and is this kind of the same problem that was already considered in the paper that I started showing you in this lecture, is what we call the hydrothermal dispatch. In the hydrothermal dispatch, we have to figure out whether we are dispatching or not. And what do we mean by dispatching? We have a demand for energy, and we have a bunch of generators. Here, just hydro generators and thermal generators. And you have to figure out whether you're going to use your thermal generators, which cost money because you have to buy fuel for them, or if you're using your hydro generation, which don't seem to cost any money because you can just use water that comes from rain and there is stored in your reservoir. So, okay, you want to figure out which ones you're turning on, your hydro plants or your thermal plants. So let's analyze things that might happen in both of these cases. So in the first case, you could think, okay, let's not use our reservoirs because we love the idea of keeping them full of water. So yeah, you could do that. That could be a decision that you might take. And something might happen in the future. For instance, you have a wet future flow, which is whatever water is going into your reservoir. So there's a lot of water coming into your reservoir. And if you kept your reservoirs full and a lot of inflows came in, you'd be throwing out that water. So water that could be useful to generate energy is going to be spilled, thrown away. However, if you took the same decision, but something else happened with the uncertainty, so you didn't get any water coming into your reservoir, then you did a nice operation. You did an economic operation because, yeah, you use your thermal plants, which are not cheap, but you also save water that can be useful for you in the future. And you didn't throw away any water because, yeah, there was nothing extra coming in. On the other hand, you could choose to use your hydro plants and, yeah, bring down your reservoirs. If you did that and there was a wet period, so a lot of water coming into your reservoir, it's just replacing the water that was already there. So again, you did an economic operation. On the other hand, if you use your reservoirs and there's a dry season coming ahead, you might even face a problem where there's energy deficit because you might not be able to attend that load that's in the system. So solving this type of problem, and here I'm just showing the two-stage nature of that. So do a decision right now and then see at the consequences in the near future is a interesting problem. And the paper that I showed is mostly focused on this kind of problem. The next step on that is understanding also the multi-state nature of it. And the idea is, yeah, this exact same decision that you have to do every single day is actually coupled in time, and you have to be constantly redoing that decision. So today, somebody that is operating a power system have to decide, am I turning hydro plants or thermal plants? And tomorrow they have to face that same decision again, and so on and so forth, for a very long time. Here I'm talking about hydrothermal problems because, yeah, that's a kind of an interesting example. But this can be, like Andrew was saying in the beginning, many other types of problem that also face uncertainty and are coupled in time. It could be, again, in the energy space, like I like. It could be a battery operation. But it could also be planning a trajectory of a robot. It could be figuring out how much newspaper you're storing in your warehouse so you can sell that in the future. So there are many different kinds of problems that are in the same scheme. Okay, so for the case of the hydrothermal dispatch, what do we have? We do have time coupling, which is the multi-stage nature of the problem. So this basically means that any decision you're doing today will affect you again in the future. Second point, you have uncertainty on your problem, which is where the stochastic word comes from. So associated with that, you have different flows coming into your power system, for instance. Or if you're talking about a robot planning, somebody might be disturbing your path. If you're talking about battery planning, a different price might be realizing. So different uncertainties might happen and affect you. Now we just said multi-stage stochastic. It's missing either optimization or programming. And here I want to focus on the case that we have special constraints for modeling our problem. In this case of the hydrothermal dispatch, we have hydro cascades, power networks, regulation rules that you have to follow. And all of that is usually solved by optimization or linear programming or nonlinear programming, something like that. And it will be a key feature of our problem. And in this case, yeah, most of about what I'm talking about, hopefully linear programming will be enough, although you can do some other stuff. And here is a point that I was even talking to Andrew a little bit sometime before. I think here comes one of the relations with something that you have been studying, which is some classic theory of optimal control. So when you're doing optimal control, you have typically a cost function, you have time coupling, you can have uncertainty if you're doing something like Kalman filter or the linear Gaussian regulator. But in most of these cases, you do have some very special types of constraints, which is equality constraints representing your dynamic system. So basically saying that, yeah, if you know your state, you know your incoming state, and you know the control action that you want to apply over there, you can just multiply some matrices and vectors. So in theory, it's something very simple to do. And then you come up with whatever is your next state, whatever is going to be the next step on your problem. And we'll be coming back to that a bunch of times. But one thing is usually missing in the classic description of for instance, the linear quadratic regulator problem, which is inequality constraints. And that's why I was detailing linear programming in the very beginning of this class to highlight the fact that inequality constraints are over there, and for many of these constraints to be well represented, you actually need those inequalities. And that's one of the things that make solving general multi-stage stochastic programs so different. Well, not so different, but different from the linear quadratic regulator problem, for instance, because you have these polyhedral constraints, which are not cases where you can kind of analytically come up with a recursion rule for. You have an optimization problem like you were seeing, like you saw solution methods for that. And you typically need an algorithm to solve this type of problem. No analytic solution is usually available in the general case. So go on, please.
Can we just add some comments on this?
Please do.
So in the previous lectures, we learned about optimization problems that he said. Those optimization problems, this is an optimization problem, right? So in theory, if you make some assumptions, you could write this all as one big optimization problem, right? And Joaquin will kind of tell you why that's a bad idea, right? Why this is writing this as one single optimization problem is not the way to do it, right? Then we looked into very special cases, as he said, of these problems that don't have inequality constraints. And we were able to derive very efficient solution methods for those, right? So the Riccati recursion that we kind of like looked into the previous lecture, it is one of those ways that he talked about, right? Like you write this recursion, you analytically define this recursion that if you perform, it's gonna, in a very small number of steps, it's gonna give you the optimal solution much faster than if you just ran Newton method on the larger case, even for the deterministic case, right? Now we have uncertainty and the problem becomes much harder. So not only we have inequality constraints that avoid us from kind of defining optimal solutions, but we also have these very impactful uncertainties. So those things together, they will kind of like define the reason why we need such an approach that he will present, and why it's a very important thing and very impactful that in that sense. Does that make sense for everyone? Is that more or less clear? Was it clear for you why we were talking about single shooting Newton method in the previous lecture, as opposed to what not just write an optimization problem? I only see heads like this, but no.
It's about exploiting structure, right? So we're looking at a particular class of problems, and you would hope that we have some better way of solving it than just defaulting to the generic approach. So those were kind of the domain-specific ways of addressing it.
Exactly. And now we're gonna see a more generic case that allows you to do very hard constraints. For example, avoiding that your lines in power systems, they burn up, or avoiding that you are not able to like respect stability constraints or whatever, right, in your system. So now we have this very elegant way that he will present to do this. And it will have a lot of connections to the things we talked before. And I hope that you guys try to find those connections to the methods. It's going to be like a transformation of those methods. Sorry, Joaquin, thank you very much.
Yeah, perfect. So now it's the perfect point for us to go deeper in what Andrew was mentioning, but for now, without adding the stochastics. So I will just talk about multi-stage programming, which is not a subject that you see all around, because it's kind of not so sophisticated. And when people talk about, multi-stage programs without uncertainty, they just call it linear programming, or some optimization thing that has many steps. But they usually just write that at a single optimization problem. However, if you want to go in the direction of better understanding multi-stage stochastic, I think this is an interesting in-between step, which can help a lot. And the interesting thing is that one method to solve that kind of problem, multi-stage problems, without uncertainty for now, is simple dynamic programming. We'll see a basic example of dynamic programming, and then we will make it more and more sophisticated throughout the rest of the lecture. So before going to multi-stage, let's first look at the first step towards multi-stage, which is two stages. Instead of having one single stage problem, linear program that like I was showing before, let's see a program in which you have two stages. So now I kind of split my decision variables in two main types. There's X, which is what I call a state variable. So it's a variable that will carry information from one stage to the other. And there is U1 and U2, which are my control variables. So the variables to define what I'm going actually to do and what is actually going to happen in the given first and second stages. And of course, each of the variables are associated with their costs. So there's D1 for U1 and D2 for U2, and you can have some costs for your state variable as well. Here, I kept the dynamics of the system. So yeah, linear dynamics. However, I said, for instance, that the controls that you have to do, they have to obey this greater than equal type of problem. This is already generic enough to encompass all reasonable stochastic programming problems, as long as you write the proper B1, A1, A2, B2 matrices. So yeah, you can see that already that there is a special structure in this kind of problem. It's I tried to write it in a way that you can see that the problem is actually kind of block diagonal in some sense. It's not exactly diagonal, but it's almost. And that is kind of some structure that we'll be exploiting implicitly when we will do decompositions of these type of problems. So this is already me going slightly ahead in terms of some slides. Okay, now that we've seen in detail two stages, we are ready to go for multi-stages. So what I basically did over here is that I added, I added 3 dots because yes, and I actually forgot the ends over here. That's fine. So now you have multiple state variables and multiple control variables, each one associated to a period going from 1 to n. So you can go, yeah, do something today that will convert in the next state for tomorrow, do something else tomorrow, and then go to the next day, and so on and so forth. The first issue that appears here is that this problem can grow a lot depending on the number of time stages that you have. It's a interesting trade-off because you were, like Andrew was saying in the beginning, you studied Newton's method, for instance. And you've probably seen that the Newton method does not scale linearly. So for instance, it has like a, I don't know, cubic number of steps that you have to do. I think even more than cubic number of steps that you have to do to converge the algorithm and to find a solution. So if the number of steps that you have here grow a lot, the number of steps that your optimization algorithms will take to solve this problem will grow linearly with that. And this might make this problem very hard to solve or even impossible to solve in some problems. This is not a very bad scaling problem because as you can see, you're increasing linearly the size of the optimization problem, although the solution time is polynomial on that, not linear. Your solution time will grow a lot, but that's not the worst kind of growth in complexity that you could have. You probably have seen cases where you have exponential growth in complexity, which is much worse than this. But the main message is that you clearly can see that there's structure in this problem, and we hopefully can exploit that structure to solve this problem in a better way. A note about practicality of these things is that many times when you're doing deterministic, this is not a bad scaling problem. However, knowing how to decompose a deterministic problem is the most complicated step that you have to go through when you're talking about the stochastic programs that are much more complicated than this, and are the ones that actually grow exponentially more complicated. Okay. So yeah, like I was saying, the problem can be too big. If the problem is too big, what you can do, you can decompose the problem. This comes from past ideas, even when people have these very small computers. You can talk to your grandparents or parents sometimes about that, and they will tell you amazing stories of how they lived with a 10K byte RAM on their computer, which for us is like, what? Um, but fair enough. People in the past had problems that they couldn't fit even in the RAM of their computer. Nowadays we can do much bigger, but even though you can always think of bigger problems, and there is always a point in which you have to decompose your problem to do that. So if you have that kind of big problem, at least my automatic reflex as engineer, so my engineering side would say, yes, let's try to break that problem in smaller pieces. And then try to stitch them back together. So solve the small pieces and try to connect them in some way. So this will be the crux of the most of the things that we'll be doing. Go on. Somebody wants to say something?
Can you go to the previous slide?
Yes.
So I know that you represented the state and the control variables separately, and we're just doing multi-stage but not stochastic. But how are you only assuming that the state carries on between the stages, but the control of the previous stages don't affect the next stages?
Yeah, they affect implicitly because whatever decision you're doing here in stage one, so you start from your initial condition, x0, and whatever decision of the control that you're making for this u1 over here will at least indirectly affect the state that you end in that stage one. And this x1 will go through the next step. So yes, we want to keep the structure of the problem in which U does not communicate directly with all the other stages. However, it communicates indirectly because it will affect the state variable just nearby, and by consequence, affect all the others. Does it make sense?
Thank you.
Awesome. Yes, great question, by the way, and keep asking for that. Sometimes I go fast about some of these things. It might not be super clear. And like I was saying, when we want to decompose the problem, let's break it in small pieces and try to stitch them back together. And well, the first idea is that, yeah, great, let's break our problem and then stitch them together, but how exactly? And the idea here is to, yeah, let's try to solve the problem all the way at the end and try to move that information from the past to the present until you have all the information that you need today, so you can take you can solve the problem. So you're kind of back propagating the information from the future to the present. And how to do that? You need to do something that we call represent the future stages as a future cost function or a cost to go function in earlier stages. So I will make that mathematically clear in a second, but the idea is that you're solving a problem today and you don't know about all these other steps because the problem gets too big. So you try to approximate or represent all this idea of a future in a function that represents all the costs of the future. And this is an instance of what people call dynamic programming. So let's try to make it more mathematically clear what I mean. So dynamic programming is a term that was coined by Richard Bellman when he was in the Rand Corporation in the 50s. And it's a very powerful concept that actually stands to many, many areas. It doesn't have to be connected with multi-stage problems. So people use dynamic programming in problems that are not actually multi-stage problems. There are, for instance, people use dynamic programming to solve combinatorial optimization problems in a clever way, for instance. There's even a interesting fact about dynamic programming. I can send you a link afterwards. There's a very interesting paper about Richard Bellman talking about the origins of dynamic programming and why he chose the word dynamic for that. And the response is actually slightly fun because it kind of says that dynamic gives a sense of movement, yes, but also it says that dynamic is a word that basically always have a positive connotation. So he was coining a term that for everybody that had no idea what dynamic programming meant would say that, yeah, that seems an interesting thing because dynamic has usually this interesting positive connotation. So it was part of him playing with words altogether. Okay, anyway, going back to the math. The decomposition proposed in the case of our problem is, let's break that multi-stage problem into smaller pieces. And yeah, natural pieces are exactly each of the stages that we were talking about before. So here, I'm taking that big problem and just grabbing a single stage of that. You can see here that there's the past state. Oops, my bad. There's the past state over here in red. It is multiplied by a matrix like it was before. There's this constant on the right-hand side. And then you have your control variable and your state variable. So whatever you choose to be your control variable will affect the future of your problem, which will be connected to this state variable over here. And what I meant by future cost function or cost to go function is exactly this alpha function over here. So if you know this alpha function, you can solve a single stage problem, and whatever goes to the future will go into this x variable and will go to this alpha function over here. So if you know the alpha, you can solve the problem, which is a very small problem, have an idea of what will happen in the future, and move to the next state. And of course, alpha is a parametric function, so it's a function of the state variable. So just like you're looking at the future over here, this entire problem is representing by itself the future cost function of the previous state, of the previous stage of the problem. So depending on what comes into xt minus 1, there will be a problem over here for xt. And then xt will be solved, and then you plug that in the next alpha. So you actually broke your entire problem in these smaller pieces, and the future cost function is what is coupling them together. Okay? Okay. Now let's take a quick look at an example of dynamic programming so we can make some of the computational aspect of that more concrete. So one of the steps towards dynamic programming is, well, this is very basic dynamic programming, and we will move fast into more sophisticated things. But the idea is that you start from a full reservoir. So these buckets over here are reservoirs. And this case means a full reservoir, full again. This is a half way full reservoir, and this is an empty reservoir. So what I'm trying to represent here is that if you have a full reservoir and then you turn on all your thermal plants, you will stay with a full reservoir in the second stage. However, if you turn on just one thermal plant and the other one was a hydro plant, then you use some water, so you finish your first stage with a halfway full reservoir. And if you just used hydro plants, then yeah, you get to the next step with an empty reservoir. How we can use dynamic programming? What is the mechanics of that to solve this kind of problem? The idea is, yeah, well, first we have to figure out what are the costs of turning two thermal plants together, just turning one or turning zero, and so on. So if you're turning two thermal plants together, you have a cheap one that costs 1 unit, and you have an expensive one in red that costs 10 units. So turning on both costs 11 units. Turning on just the cheap one plus their hydro plus costs overall 1 because that's the cost of the thermal plant plus 0 of the hydro. 2 hydro costs 0, but will leave you with an empty reservoir. And the same repeats for all the cases. So when you're doing dynamic programming, like I was trying to explain, the first thing that you do is that you go all the way to the last step that you have to solve. In this case, the last stage of the problem. It's a 2-stage problem, 3-stage problem because, yeah, depending on how you count stages. But anyway, let's go to the end, to this last stage over here, and let's see what can we do. If we started this last stage with a fully full reservoir, what would be the cheapest thing that we could do to solve the problem? Well, the cheapest thing we could do would be turn on 2 hydro plants. If you started this last stage in an in-between case, what is the cheapest thing that you can do? Well, in that case, the cheapest thing that you can do is 1 thermal plant plus 1 hydro plant. If you started empty, you don't have much of a choice. You have to turn on only the thermal plants. Okay, now you know what would be the cost if you ended the first stage in each of these cases. So what we are doing here is that associated to this initial state over here, full reservoir, we know what's the future cost. The future cost from a full reservoir at this point is 0. The future cost of a halfway through reservoir at this point is 1. The future cost of an empty reservoir is 11. So this is us coming up with our future cost or cost to go function. Now that we did that, we can go one more step in the past. So let's see what happens. We could go through this step over here and pay 11 because of our two thermal plants. And then we know that our future cost would be 0. So 11 plus 0, 11. If you go through this other path over here, it would be overall, well, I missed a number over here. It should be a 2 over here. It would be a 1 because of this thermal plant over here, plus 1 of this other thermal plant over here because you know the future cost of ending your problem at this point. So this would be a 2. And if you use 2 reservoirs over here, it would be a 0 in this stage plus a future cost of 11. So your entire cost is 11. So it would be 11, 11, and a 2 over here that I make a mistake. 1 because of this one, 1 because of this one, overall a 2. So what you would do at this point is this solution. So overall, you solved your multi-stage problem by solving only smaller pieces of this. Of course, this is a small problem. You could easily compute that by head. It's not complicated, but the idea is to show this multi-step type of solution of a problem. You go all the way to the end, you come up with a cost function for the future, you bring that information. Now you don't need to know details about the future again, and then you solve the problem of the present, just knowing this future cost without having to know all the details that go into over there in the future. Okay, so this is dynamic programming. However, dynamic programming suffers from something that people call the curse of dimensionality, which basically means that solving with dynamic programming problems that are too big can be exponentially more complicated. And let's see what the issue is. So suppose we have a single reservoir and two possible water levels, but now we have 11 stages. Just like here, we have a single reservoir, three possible water levels, and 3 stages. We kind of have a 6 over here, but that could be easily something in the order of magnitude of a 9. Because the thing goes combinatorially, opening up many possibilities. So if you're in this case, you have something in the order of magnitude. It would be less than 1,000, but it would be something in the order of 1,000 possible paths that you need to check. And you could think of something that is even worse. So what if you have 80 reservoirs, 60 time stages, and 10 different levels of your reservoirs? So you can easily see that, yeah, even for just one stage, if you have 80 reservoirs, 10 different combinations of level for all of them, and then you have to solve that in 60 times in the past, enumerating everything won't be a possibility. So this is the fail of enumeration and a challenge of dynamic programming. Because we're talking about multiple topics over here, maybe this is a interesting point that we can comment. This is why people do things like reinforcement learning. So when they're doing reinforcement learning, they're trying to also do some sort of dynamic programming with this time coupling. But they're trying to explore this infinite amount of possible paths in a clever way, which is the thing that people call the exploration and exploitation trade-off. So how much you explore different paths, because you won't be able to explore all the possible paths, and how much you explore, how much you emphasize the paths that you already know about. You compute the best possible solution in the paths that you know about. So in more classic reinforcement learning, you also be trying to come up with cost to go functions and detail them. And the basic, most simple way to do that is by enumeration via dynamic programming. But that can be especially challenging. Okay, so this is to try to bring the concept of dynamic programming. So we can go to the next step, which is what I call dual dynamic programming, or a nested Bender's decomposition. Okay, so interestingly, dual dynamic programming is not something that showed up before stochastic dual dynamic programming. It was not, dual dynamic programming was not a thing before stochastic dual dynamic programming. However, this is a useful concept that, at least I think so, sometimes make it easier for us to understand the more complicated version of the algorithm. So dual dynamic programming will be an algorithm to solve multi-stage deterministic problems that, for instance, there are problems that are so large that don't fit the memory of your computer because they have so many stages. So you have to break the problem into smaller pieces. So let's see more details about that. Before going through all the details in the case of a multi-stage version of the dual dynamic programming, let's try to quickly understand what is the single stage version of dual dynamic programming, which is basically what people call Bender's decomposition or Kelly's method. So this is Bender's decomposition or dual dynamic programming in 2 stages. Is an algorithm to solve a 2-stage problem. So here I'm bringing back our 2-stage problem, which has a state variable x again, has our control variables u1 and u2, and I colored them in slightly different colors to try to show that, yeah, let's break this problem in 2 pieces. How do we do that? This way. So here we broke the problem in 2 different pieces. We have a piece for the first stage. So you can see everything about the first stage over here. So what you can see over here, the control of the first stage, the state variable, and the dynamic of the system. Whatever you do with the U will lead you to a different state variable. And this is a linear program, but has this future cost function that represents whatever happens in the second stage. And below here is the second stage. You get an X, which is an input of this optimization program. So you have this optimization program is a parametric program in X. So for all possible different values of X, give me a value of X, you can solve this optimization problem, you can know the value of the alpha function. So alpha is clearly a function on its own. For every possible value of X, you have an objective value of this thing over here. So yeah, alpha is a function. So we could, in theory, try to solve this problem. And let's try to think of how would we solve this type of program. So let's take a peek on the definition of alpha, which is basically the parametric solution of the second stage. And let's try to understand some interesting things about that. Okay, so what is alpha? I'm just repeating over there what was in the previous slide. This is the definition of alpha. To obtain the value of alpha, you have to solve this optimization problem, which is a function of alpha, of x. X is an input data, so it's a number. So all this thing here is a number. And then you have to solve this optimization problem. And I will keep this notation here just saying that pi is the dual variable associated to this constraint over here. Okay? So about alpha, alpha is a convex function. I think that's a nice homework. Just a suggestion as a homework, prove that alpha is a convex function. It shouldn't be so complicated, but I think it's a nice exercise if you haven't already done that before. And the other interesting thing is that we can obtain the value of alpha and alpha prime just by optimizing the problem. So if we optimize this problem over here, we can obtain the value of alpha, but we can also obtain the derivative of alpha. And how would we do that? As follows. Here's the value of alpha. You just solve the problem, you get the optimal solution of the problem, you plug that, and you even have this extra information here. If you solve the dual version of the problem, this would be the value of alpha as well. So yeah, the value of alpha is easy. And how about the derivative of that? Well, the derivative of alpha with respect to x, which is the input variable of alpha, you can decompose that into using the chain rule. So you can compute the derivative of alpha with respect to the right-hand side of the problem, and then compute the derivative of the right-hand side of the problem with x. But we talked about in the very beginning of the class that the derivative of alpha with respect to the right-hand side of this problem is the dual variable. So this thing over here, by duality, is the dual variable. And the derivative of this simple function over here with respect to x is just minus a2, because this is a linear function. And the derivative of a linear function is just doing that. So by using duality and a simple derivative of a linear function, you have this thing here being the derivative of alpha. Okay? So,
Joaquin,
yep,
can we
please.
pause one second? I know that a lot of people know about duality and all these things, but is this clear for everyone? Is this, he jumped back into his definition of duality, he grabbed things there, and he's placing as how to calculate this objective function and the derivative for a fixed input x, right? Is that more or less, do people understand the step that he did? Pedro, who's not from an optimization background.
I mathematically understand,
Okay.
but I don't fully understand duality here. And I think that's something that is not gonna be solved right now. But like the mathematics, I
It
can.
makes sense. And although strong duality, he never proves that, like that there's this relationship between the primal and the dual problem. But you remember Lagrange multipliers.
Mhm,
This is the Lagrange multiplier.
Which is the lamp.
We in many cases level here is the pi.
Yeah,
Yeah.
We defined previously it.
Exactly in the previous lectures.
Yeah.
Perfect.
Yeah.
Go ahead.
So yeah,
Does this
pi
only work
is,
for the?
Sorry, Joaquin, we have one more question.
Yeah, go on, please do.
Does this only work for the optimal x, like the derivative?
Yep. You can only compute the derivative this way for the optimal solution.
Do you mean Ivan, do you mean the optimal x star? Or do you mean the
okay.
optimal
Yeah.
lambda of the optimal pi?
Oops, my bad. Sorry. So yeah, let me stress this a little bit. So there are two possible ways we can talk about that. So for any x, if we want to compute the derivative of alpha or the value of alpha with respect to that x, we solve this problem, we get the value because it's, yeah, by definition is that. And if you want to compute the derivative, yeah, this star over here is not helping. It's actually not helping at all. So yeah, just disconsider this star over here. I'll fix that in the next one. Maybe that's the source of the confusion. So you can only compute the value of alpha after you solve this problem to optimality. But it doesn't have to be the x that solves the two-stage problem that we were seeing here. It can be any x, provided that you solved this problem here to optimality. Okay?
Distinction is alpha x is only defined after you solve, after you get the x star. But after that, you're saying it needs not to be the x star that gets evaluated in this alpha requirement. Is that what you're saying?
X is not decision variable.
Yeah, x is a parameter over here. So let me actually.
I think a good way to put it, and Joaquin, correct me if you have a better way, is alpha is a function that depends on the solution of the second stage problem. That makes sense. So the first stage, we are using alpha to make the decision in the first stage. So
Yeah.
the second stage decision doesn't really matter. Like we are defining this second stage just as a way to get the value of alpha. And then in that way, yeah, it's defined for any possible x that can enter there. And it will be used to make the decision about x.
Give me a second. I was just doing some stuff over here. Oops. So yeah, it's exactly like Andrew was saying. X is an input to this optimization problem. We are solving here just a parametric optimization problem with where this X is an input to it. So you can choose whatever values of X you like, 1, 2, 3, 4, 5. You can solve this optimization problem. This will be the value of alpha. And I'm telling you, yeah, you can also compute the derivative of alpha in an efficient way if you use duality. So that's the core of the thing. And this thing might look complicated, but we can also spend some extra time over here or come back to this later on if you need. But this is the key idea that will be used all around. So again, I'm here defining a function alpha. For each x that you give me, you plug the x over here, you solve this optimization problem that is predefined because b, big B, small b, big A, small d, these are parts of the definition of this optimization problem and they don't change. So for every different x that you give me, you can solve this and this will give you a value of alpha. In theory, you could compute the derivative of that by finite differences or by the definition of derivatives. But there's a clever way to do that if you know a little bit about duality. That's the key of what I'm trying to convey over here. Okay? Okay, so feel free to bring me back to this point if you get confused in the future. But that's the idea. So now that we talked about alpha, let's go back to our first stage that uses alpha to solve the optimization problem. Okay? Well, we can convert this first version of the problem into the second version over here. And what I'm doing at this point, I'm just changing this to be a general function. Now, this is a decision variable. Alpha now is a decision variable over here. And this decision variable follows this constraint over here. Okay? And this constraint over here is a piecewise linear constraint where the beta is the value of the function evaluated in x of y. And gamma is the derivative of the alpha function. So let me do that online with you. Go on, Andrew.
Alpha here now became a variable. So
Yeah.
in the second guy there, when he's just, I think you missed putting alpha as a variable as well on the right hand, the right problem, right?
Yes. Let's do it together over here. More details because I noticed this is not as clear as I wanted it to be. So like Andrew was saying, there's alpha over here. Fair enough. There is a of alpha of x I over here. and there is alpha prime of xi over here. Then I have to add some spaces because I have to align this thing. That's it. Okay. I'm still sharing, right? Yeah. What is over here, like me and Andrew were mentioning? Now we have this alpha as a decision variable instead of being a general function of x. It's just a decision variable over here. If you're into optimization, this is an epigraph variable. And alpha has to follow this constraint over here. So I'm just saying here, this might be a slightly long sentence, but alpha, this variable here, is greater than the first order Taylor approximation of the function alpha, because this is alpha evaluated at a given point xi. This is the derivative of alpha at a given point xi, and this is the difference between x, which is a decision variable, and xi, which is not a decision variable. It's just a point that you sampled from the future. So this is a rewrite of this first problem over here, where this function is not a general function anymore. Now your entire problem is a linear function. It is a linear program because alpha is a variable and this is a linear constraint. Alpha of xi over here is the value of alpha evaluated at the point xi, which is not a decision variable. Alpha prime is the derivative of alpha evaluated at xi, which again is a point and not a variable over here, times the difference between x and xi. So this is the first order Taylor approximation of the problem, of the alpha function. My bad. So let's see now a little bit of how we can approximate this alpha function iteratively using this idea of representing alpha with linear approximations, which are also called cutting planes or Bender's cuts. Okay? So what do we have over here? We have a function in blue, which is the actual alpha function. Okay? But we don't know that. And we have in gray over here a bunch of linear approximations of that function in terms of cutting planes. So what does it mean? It means that we are creating a bunch of linear constraints that are always, this thing is broken here, my bad. Let me delete this. For some reason it showed up. So there's a bunch of linear constraints like cut number 1, cut 0, and cut 2 over here, which are representing this blue function that we don't know. So we know the cuts, but we don't know the blue function. And the cuts are just defining a feasible region. So this entire thing here is the current feasible region, because we don't know the blue thing over there. So if we want to solve this problem and find this solution over here, the best thing that we know is this thing, because we will be trying to minimize something. We go this way, and this is the point that minimizes in that feasible set. Okay.
Can I say something?
Please do.
The alpha variable is a variable. So for example, if our x is scalar, alpha is also scalar. And we are saying that it should live above this red line, right? So it's although it's a scalar, it's representing a whole space on top of that function. That's why he called it epigraph, right? It's an epigraph variable. We are writing in this way, and it's okay if it's not obvious for anyone that hasn't seen this before, but it's more or less, we are having like a poetic license, because we are not showing the dimension of alpha here. We're just saying that for every powerful value of x, we want alpha, which is a variable, to be on top of these things. So it's almost working as if it's a function, although it's a scalar value. Because for every value, possible value of x, alpha has a value. Is that clear? Yeah, nice. As he put it there, alpha is a function, both the blue line, the original function, and also the variable. It's representing the function value, but it's a scalar in our optimization part. Thanks, Jordan. Sorry.
Yeah. That's the difference between the blue alpha, which is the blue function that we don't know, and the red alpha, which is a variable that is being minimized and it's reaching this point over here. So what we do is that we solve the master problem. And what was the master problem? The master problem was this thing over here. This was the master problem, which is the same as this, is the problem of the first stage. Okay. Where we only know a few of these cuts. So we start from our arbitrary iteration, so we have some cuts over here already. And then we solve the master problem, first step. But the issue is that we only know the cuts 0, 1, and 2. So for us, the best representation of the function is this thing in red over here. So we get to this solution over here. So now we go to this point that we went, and now we can evaluate this point x3 over here, because x3 lies in this axis over here. Because this is the x-axis. And then we pick this x3, we plug it into the second stage problem. So we plug it into that alpha of x equals to minimize c of u, subject to something like, I don't remember by heart, sorry. It was like bu equals to a small b minus a x. So we'll try now x3 over here. So plug x3 over here and find the new value of alpha. So you find this point over here. But like I was saying, besides knowing alpha, with the dual variables, we also know the derivative of alpha. So we can create a new cut over here. So that's what we're going to do. So yeah, we compute the new upper bound over there, and then we can use the derivative to come up with a new cut to better represent the function. So now the representation of the blue function that we don't know will be something like this. Okay, so this thing is not valid anymore because that cut this part of the problem. That's why we call it cuts, because it removed this part from the unfeasible region. And what we do now, we keep iterating. So now we have the cut number 3 over here. We solve it again. Now we get to this point. What we do now that we get a solution from our master, we get a new x4 over here. We plug that into the second stage. We compute the value of alpha, which is this point over here. And then we can also add a new derivative. Here is the new derivative. Oops. And now the valid function for us is this thing over here. Fair enough. And now we optimize and get to the optimal solution. So you can even see that there are some parts of the problem that we did not approximate correctly. So this thing in green over here, all this other area in green, and this other green area over here, they are not perfectly represented by our cutting planes approximation, by our red function approximation. However, the solution is properly supported by cut number 4 over here, and cut 0 over here. So when we solve it again, we'll get to this point. And then we will evaluate the second stage problem. And then we just find, yes, you are in the correct solution. So that's when the Bender's algorithm finishes. Okay?
Isn't
So
it
this-
sort of like the bundle method?
It's not exactly like the bundle method, but there are similarities. Yes. Yes. In the bundle method, maybe we can talk more later about the bundle method. Otherwise, I think we can diverge. But it's similar to the bundle method in the sense that you're kind of iteratively improving the solution of your optimization problem. Okay? By gathering information, new information at every new iteration. Fair enough? Okay. So now that we talked about Bender's, which as I was saying, was the 2-stage dual dynamic programming algorithm, let's talk about the multi-stage dual dynamic decomposition algorithm. So now we'll just have a nested set of that Bender's decomposition. So the dual dynamic programming algorithm is an iterative algorithm as well. That consists of 2 main phases, okay? There will be a forward pass or simulation where you learn how to go to the future. And then there will be a backward pass where you bring the information from the future in terms of cutting planes. We have already seen that working in 2 stages. You solve the first stage, you have a foresight into the future, which is the X state variable. Then you evaluate that. And then what you do, bring that information back to the first stage. And then we went back and forth in a 2-stage problem. In a multi-stage version, let's see what happens. So now I'm bringing an animation that I actually adapted from a late professor of Georgia Tech called Shabir Ahmed. He was the first one to show me this way of looking at the dual dynamic programming algorithm. And this is basically a multi-stage version of the Bender's algorithm that I was showing you guys before. So in some sense, this will be a little bit of a recap and a new version of the problem. So what we're doing, we start solving the first stage problem. So we have our initial condition over here, right? We solve this problem, and what comes out of the solution of this problem? We get x1, which is the solution of this problem, right? The final state, because this was the input, this was the control, and now we get this state that is evaluated in some sort of approximation of our future cost, which here is represented in terms of these blue functions, shaded blue functions that are unknown. Just like the Bender's function was unknown, this is just representing the correct thing that we'll be iteratively approximating. So what happens with this x1 over here? We can plug that into this alpha2 function, but for now we don't know anything about it. So we just have this point over here, okay? We don't know nothing. So what we do, we go to the next stage. So now x1 that was over here is our input. We solve this optimization problem. We come up with x2, which is here. Fair enough. We're just moving forward in time. Now we grab that x2, we plug it over here, we solve the optimization problem, we get an x3, and x3 stops over here. So we went all the way from the beginning to the end. Fair enough? This was the forward pass, because we started in stage 1 and solved all stages until the end. Now we're going to go backward in time, right? Like we were mentioning before. How do we go backward in time? Now we are solving stage 4 over here. And this is an x4. Now we're solving the problem of x4. There's no future cost here because it's 0. Because this is the last stage of our problem. There's no future cost after the end. We are solving a 4-stage problem. There's no future. So we grab this x3 over here. We plug it in the stage 4. Okay. Then once we solve the stage 4, we come up with a pi, the derivative. And we improve the approximation from below of this alpha function over here. Okay. What do we do now? We were in stage 4. We go back in time once more. So what happened over here? We grabbed the x2, plugged into the optimization problem, solved it, got a pi4, pi2, and improved the approximation from below of the blue function. Okay? And what we do? We continue going back in time. So we improve the approximation of the first stage. Now, we start again from the beginning, but now we know a little bit more about our functions. So instead of in the first stage, starting from x0, instead of going here, which was the first point that we attempted, now we say, well, if you go here, there will be a cost. If I'm trying to minimize, let's try to go here. So we'll be exploring a different path. So we can go here. We'll optimize the problem, find the next one, and go here. And what happens? We keep going. Oops. We go further in time. Now we have this x1. We plug as an input. We solve the problem. Again, here was the cutting plane that we found. So we optimize and go here. Now we proceed with that. We take this one, this is x2, solve the problem, x3, go here. So we are exploring another path forward into the future. And then we go back again,
Rocky?
Oh, I have a
building
question.
the cuts. Yeah, go on.
So in the two-stage vendors, right? The cuts are guaranteed to be tight, like with the like when approximating alpha, right? Could you explain why the cuts aren't tight for? Yeah, that's a good question.
Yes. That is an excellent question, and that's something I was going to comment to check if you were seeing what I was trying to bring as information in this figure. So if I don't know if everybody have noticed, but when I was doing Bender's decomposition, and sorry for going back at it, every time I added a new cut, the cut was always touching the function. So here's the cut. It's always touching the function. The second cut I will build will be over here. So the cut will touch the function here again. Here is the red dotted cut touching the function. Okay? And what was just observed in detail was that when I went to the last stage, I wrote a tight cut over here. Does it make sense? Just like I was doing before. But when I went back one stage again, the cuts that I created has a small gap between the actual function and what is happening over here. And the key question that was just asked is why you kind of left that information over here, over there, and why is this relevant somehow?
Rocky, can
Yeah.
we ask that to the students to see if they have an opinion? Why that happens?
Please. That's a
I have a guess.
interesting thing.
Yeah.
So like alpha 3, like depends on the approximation of alpha 4. So because that is incomplete, there's the gap.
Exactly. And
Exactly.
because we are always approximating from below, then this gap happens because of this, right, Jerky?
Exactly. You don't have the full information of this problem over here. So because you don't have the full information and alpha 3 depends on alpha 4, unless you have all the cuts ready over here, you might have a gap over here. If you had stopped and, yeah, let's create all the possible cuts over here before going backward, then yes, then you could have a cut that was tight. But otherwise, by the exact same reason that you said, that happens. It's because this problem was not perfectly approximated yet. So the idea is that you go iteratively going back and forth. So going forth and then backwards again, improving that approximation. And when you keep doing that, you move that information from the future to the past, to the present, iteratively. And the cuts will be going up for the initial stages. And at some point, this will converge, and the last cuts that you add will be actually tight somewhere over here when the algorithm stops. Okay? That was an excellent question. And that's actually a discussion point that even people that have worked with SDDP sometimes for more than a year don't notice this kind of issue. So yeah, it was really great that you observed this point. That's something that I always try to convey, because some people, they work for years in SDDP and they don't notice an important thing like this fact. Okay. Some comments about the things that I just wrote, that we just talked about, is that yes, well, it's actually missing an R over here. We never need to solve the actual dual problems, because when we solve an optimization problem with many methods, most of the methods, they give you the dual variables as a gift. So that's actually part of the solution of the problem, and they just give you the dual variables as well. Convexity was a requirement in what we have been doing, but linearity not. Although everything I wrote was for linear programming, you could have a version of that for instance, conic programming or some convex nonlinear program. However, if the problem was non-convex or integer, these things would not work out of the box, just like we were talking about over here. There's even a version of SDDP that people call SDDIP, stochastic dual
Dynamic integer programming.
SDDIP. Integer program, yeah, that's it. Wow, it was a mind-blowing thing over here to go through that. Yeah, stochastic dual dynamic integer programming, like Andrew said. It has some fixes, but it's much more sophisticated. We don't want to enter into that right now. But yes, you need convexity for all the things that we talked about. Another key observation is that cutting planes are especially useful because they can be extrapolated. It's missing a quote over here. And what I mean by that, I mean that I just added this cut. My bad. I just added this cut over here. And you already know that the function is above this value, which is different. Well, for instance, if I just told you, yeah, the value of the function is here at this point, you could say, yeah, okay, you told me that, but I don't know anything about here. But because you have this cutting plane over here, you already know that the value at this point is worse than the value of this point over here. So the cutting plane methods is one of the interesting things about the cutting plane method is that it extrapolates, it can extrapolate from the reference point and give you some more global information. And that comes from convexity. So you're only doing that well because these functions here are convex. Other interesting points is that the solution of the first stage is a lower bound of your entire problem. Why? Because let's get to the first stage. The first stage, this problem over here, depends on alpha 2. If you have a lower bound on alpha 2, means that you computed that with a lower bound of alpha 3, which depended on a lower bound of alpha 4. So alpha 2 contains all the information of the future. So if you solve this problem, of course, you have a lower bound of alpha 2 by definition of what we currently have. So this is actually a lower bound on the solution of the entire problem. So just getting the objective value of the first stage is a lower bound on everything. Any complete solution sequence is an upper bound of the problem because it's a valid solution. So when you have a feasible solution that consists of all these points over here, you can get the immediate cost functions of their things, which is the part that is not the future part. You get the immediate parts of that. you sum of them, and this will be a feasible solution to your problem because you found a path in which you can walk. If you found a path, you get a feasible solution. If you get a feasible solution for a minimization problem, that's an upper bound. Okay? So the solution of the first stage is a lower bound, and any possible path that you find is an upper bound. So you can always control your algorithm with an upper bound and a lower bound, which is great for checking for convergence. That's not something that happens in every single algorithm. It happens in this one. Yeah, and the last point that I mentioned is that multi-stage alone is not always an excuse for doing decomposition because the growth of the problem is only linear, and doing Bender's decomposition can be slow compared to interior point methods. So the lesson learned until this point is that, yeah, decomposition is fantastic. It can help you solve problems that wouldn't fit the memory of your machine, for instance. However, interior points and simplex is usually much faster if you can put the entire problem into a single thing. The issue is that sometimes you can't put the entire problem into a single machine, and then you have to decompose. And then we will see that doing it stochastic is a great way of is where you actually need that. There's no other option because the problem, for sure, even a small problem will not fit your computer. We'll see that right now. So the last block of slides, and this is getting towards the end. Don't worry, I'm not in the middle. It's almost at the end. Let's talk about stochastic duodynamic programming, what people call SDDP. Okay. So now we have stochastics into our problem, and I don't want to spend much time in this first formulation over here of multi-stage stochastic programs. You can see that in some books, but I don't want to spend too much time over here. What I just want you to understand is that when we talk about these multi-stage stochastic programs, we are solving nested optimization problems. So when we're solving the first stage problem under this constraint over here and this objective function, we consider this future cost over here, which is the expected value of everything goes from 2 and ahead. When we solve 2, we're solving, this actually should be a 2 over here. We are solving for these other guys with other constraints over here, with this other objective function that in turn depends on the future. So you have a nested structure of what happens now depends on what happens in the future, and so on and so forth. One interesting way of writing that problem is this formulation over here. You can see that in this formulation, there's no nesting in a first glance. What's in this formulation is there's a bunch of n's over here, and by n's at this point, I want to mean nodes in a tree. So you're here, you have a tree of uncertainties. And these are different nodes. So this is node 1, this is node 2, this is node 3, this is node 4, 5, 6, and 7. Okay? And what these things are doing over here is that it's just saying that the dynamics of the problem, when you're solving for node n, so when you're solving for node 4, you want to check what the past state of node 4 was, which was node 2. So this antecessor function is just a of 4 equals 2. A of 2 equals 1. So for each node, we have an optimization problem of a stage. It has its own costs, it has its constraints, and it has its decision variables, like for the first stage over here. And each one is coupled with a past through this antecessor function over here. So the main focus over here is to bring to your attention the fact that people write multi-stage stochastic programs in various ways. The most general of them, in a sense, is the above one that we just looked over here in the top, which is this nested representation of expectations. Okay. An alternate version of that, assuming that your uncertainty is given in a tree, and I will talk a little bit more about that soon, is this other formulation over here that you just define the optimization on different nodes of a tree, and then you couple them with your coupling constraint that depends on this function over here. So the message I want you to keep from this thing is that there are many ways to write multi-stage stochastic programs. Because it's a complex class of optimization problems, it can be written as a nested sum of expectations, or it can be written as nodes in a tree that are coupled by the state variables, like this. Okay? And there's even one more way that I find interesting to know about ways of writing a multi-stage stochastic optimization problem, which is this other one over here. In this other one, pretend that you don't see anything that is below this thing. You don't see the red constraint for now, okay? In this other one, I basically took the same multi-stage deterministic constraint that I had in the past, okay? And I added scenarios. I just said that for every S, you have a multi-stage deterministic problem. Okay? There is a P of S over here, which is the weight. So over here is the very same multi-stage deterministic problem, but for all possible scenarios that can happen in the future. However, if we want to talk about multi-stage stochastic, we have to couple those somehow. Then what I'm saying is that some of these paths, they actually have to have the same value sometimes. In terms of that tree that I was writing for you guys, we had a tree like this, right? One possible path, path number 1, is over here. Another path, path number 2, is over here. Yet another path, Path number 3 is over here. And of course, the last one, path number 4, is over here. What this constraint here is saying is that for stage 1, this is scenario 4, must equal to in the first stage as well, the value of the state variable for scenario 1, and so on for all of them. Because you can see all of them must match in the first stage. So this thing, you have a bunch of different scenarios, and then you have to couple them at some points in your scenario 3. And that's so on with the other ones. Same for x1 of 2, and same for x1 of 3. And then there's another constraint for this point over here where these other two match. X2, because it's stage 2 of scenario 1, must equal x2 of scenario 2. However, they don't need to be equal to x2 because it's stage 2 again, scenario 3, which has to be equal to that value in scenario 4. So this is a third way of writing a multi-stage stochastic program. This third way is not especially useful for SDDP, but it's much used in another type of algorithm called progressive hedging. When people do progressive hedging, they will actually solve deterministic programs and then couple them iteratively with these constraints over here, which are also known as non-anticipativity constraints. Okay. Okay, now let's go a little deeper in what I mean by scenario 3s. So when you have uncertainties in a multi-stage problem, your uncertainty happens in time. So when you are today here, so for instance, stage 0, let's call it stage 0. And then many things might happen with your uncertainty variable. So it might rain or not, like we were saying for the hydrothermal dispatch problem. You might see high prices or small prices in terms of batteries. You can see clients buying more or less newspaper in the case of a news vendor problem. You can have, I don't know, different types of terrain moving or other objects moving in terms of a robot trying to find its optimal path around. So many things can happen. And in theory, many of those random variables are continuous. Not always they need to be continuous. Sometimes discrete random variables represent well what's happening. But for instance, in the case of rain, the amount of rain that is coming is a continuous random variable. So multiple things can happen in the second stage. And then all the possibilities are here. So you have many possible different realizations of the random variable, and for each one of them, you have a possible future in which you have to take a decision. And then you go to the first stage after you've taken your decision. And then in the first stage, many other possible futures will also happen conditioned on the decision that you made over here. And then you go to the next one, in condition to this decision that you made, many other possible futures could happen again. So all the possibilities of the random variables for different time stages, they grow exponentially fast. So you're in the first stage, there are infinite possibilities of random variables from the first to the second, infinite from the second to the one, and you multiply one to each other. Even if you wanted to discretize that, and that's what we are doing over here. Suppose that instead of infinite amount of possibilities from one state to the other, you just have two. So you start from here, you only have two possibilities in this second stage over here. And then, again, you only have two possibilities into the future. So if at every stage that you have, and here we have 4 stages, you only have two possible random variables happening in them. The number of possible paths defined by the number of possible uncertainty realizations would be 8 over here, because you just have two possibilities. If you have 30, you'd have 30 to the power of 4 minus 1, which is a lot. So select a number of possible realizations that you can have in any step, say L. And then the number of stages minus 1 is the number of possible paths of realization, the number of possible different realizations, the number of possible different scenarios that you could have in those multi-stage things. So for instance, choose L equals 10 and T equals 10 again. So if you just have 10 different options for your random variable and 10 different stages, you'd have like 10 to the power of 9. You have 1 billion possibilities. Even sampling 1 billion numbers takes some time in the computer. So solving an optimization problem that has more than 1 billion different nodes won't even fit in any possible computer that we can have nowadays. And that's for a very small problem in which we only have 10 possible random variables at each stage in 10 stages. And people solve problems that are much bigger than that. So yeah, the first thing that we did, because we had an infinite size scenario tree, is now that we have a finite size scenario tree. Here it only opens 2 at a time. It could open 30 at a time. But if the number of random variables is big enough and the number of stages is big, even a finite tree like this that you sampled with Monte Carlo from the original tree would be already very, very big. When I sampled this tree, I did something else. I wrote a tree that is very special, that is not the most general realization of a scenario tree that you can imagine. Not only because it only opens 2 by 2, it's because when you are in this stage over here, you can only see 2 possibilities of random noise. This one and this one. And as you can see, this one is the same as this one, and this one is the same as this one. And the same thing happens in the next step. When you're here going to here, you only have 2 possibilities. And again, this one is the same as this one, which is the same as this one, which is the same as this one. And these ones are also the same. So this is what we call a stage-wise independent scenario tree. And this is actually a strong assumption for the SDDP algorithm. So the standard SDDP algorithm will only be able to handle multi-stage stochastic programs that are defined on top of finite, stage-wise dependent scenario trees. That scenario tree can be rewritten in this form over here, which is a graph that we can write, even for large cases. Because even if we had 30 different possibilities of noises in each stage, now we only have 2. Now I'm writing a thing with 3. If we had 30, we could write that, because it's just like 30 nodes per stage. But this 3 is what people, it's not a 3, of course. It's a 3 between quotes. This is what people call a recombining scenario tree. It's just a compressed way of looking at this type of trees that are stage-wise independent. So this tree can be rewritten in this form, and we can see that paths in this tree over here, for instance, this path, correspond to paths in the above scenario 3. So 1, here from the first stage, we're going to noise 1, and then we're going to noise 2, and then we're going to noise 1 back again. Like we're saying, from the beginning, we go to noise 1, then to noise 2, and then to noise 1 back again. So that path is equivalent to this path on this scenario 3 over here. So the recombining scenario 3 is just a way of representing that stage-wise independent scenario 3 that can be so large that you cannot write that down. But this one you can write down. And now let's do stochastic dual dynamic programming on top of those trees. How we're doing that? We're going to use Monte Carlo again to explore random, between quotes, regions of the uncertainty space, so paths in the tree. We can compute upper bounds as averages of paths that we explore. And the same idea will remain. We'll propagate future information backwards through these cutting planes. So the stage-wise independent will stage-wise independence. So the fact that these things are stage-wise independent, so from any stage you can get to any of the possible noises in this next stage, will be key for something that is called, where is it? Reusing cuts, which is also known as cut sharing between paths. Because cuts must incorporate uncertainties. So what are the main steps in this algorithm? The first one is a forward pass. And in the forward path, we will sample uncertainty on the tree. So starting from the tree list that we had, we will sample a path, for instance, like this path over here. Go here, and then go here. These are the nodes. So we'll sample paths, solve these problems in chronological order, and this will be the forward pass. And then there will be a backward pass in which we'll follow this thing back in the opposite direction, computing the same cutting planes that we did for DDP before. So the forward pass is just sampling these trajectories in the recombining scenario 3. And one interesting point is that we can do these multiple paths in parallel. So you can sample a bunch of different paths in the scenario 3 and solve all of them forward in time in parallel. And of course, just like we were doing in DDP, we can compute in the backward pass the cutting planes in parallel as well. So this is actually just us doing something that is slightly more advanced. So we computed cutting planes for all these, and then we can use all these cutting planes from all different paths in the tree in the same nodes. So we can reuse all of them over here. We can reuse all of them over here again, and so on and so forth. And then we propagate back in time and generate more cutting planes. Finally, we can analyze some convergence profile. And this is a typical convergence profile of SDDP. So we have a lower bound, which is, like we said before, is the objective function of the first stage, because you're representing that as a future cost function. So in the first stage, the future cost function is being approximated from below. So you can see the thing only growing monotonically. And the upper bound are the feasible solutions that we find throughout time. However, these feasible solutions depends on the sample paths that we chose. Different from the DDP without the S. In DDP, we only follow the given path, and that was it. Here, we sampled different random numbers in time, and then solved all of them in parallel. And then how do we compute that upper bound? We take the average of them. So just like you do when you're doing Monte Carlo approximation. So this is why it's common to represent SDDP convergence with these two lines, an upper bound that is always a single line, and an upper bound, a lower bound that is always a single line, and an upper bound, which is the blue thing, and it's zoomed here over here, which is a single line, which is the average, plus a shaded area, which is a confidence interval on that area. Why a confidence interval? Because you did many paths, depending on the multiple uncertainties that you sampled. You took the average of them, so you only have an estimator. So in order for you to have a better idea of how good is your approximation, you compute the confidence intervals of that. So you know kind of the variance of that solution that you have. And after you converge that, and after you run that for a bunch of iterations, that converges when the upper bound and the lower bound touch each other. So this is a typical SDDP convergence profile that I took from this paper over here. Details about the cutting planes. And here I'm almost over. I know we have the time coming. I want to pass to you some concepts that some people find when they look at SDDP for the first time, and sometimes they get confused with that. There is what people call average cut SDDP, and multi-cut SDDP. In average cut SDDP, is just like the Bender's decomposition that we had. When we generate these cuts from all these possibilities, we have to pass them to a single optimization problem, for instance, this one over here. So we have our optimization problem, as always, and our cutting planes over here that are associated with this alpha variable that is above all the cutting planes. Okay? In the average cut case, you take all these cuts and you take their average. So you have 3 cuts over here. You're taking the average of 3 cuts before you use this cut in the preview stage. So this is the average cut algorithm. The multi-cut algorithm, which is the other variation. So yeah, a single cut is generated. Coefficients are the averages. And all these openings must be solved so you could have a single cut. In order to obtain a single cut, you have to solve all these problems over here. In the multi-cut representation, on the other hand, you have the same optimization problem that we had before, but now we have multiple of these alpha things. And each one of them is associated to a different set of cutting planes. So the cuts that came from this guy go over here. The cuts that came from this guy go over here. And the cuts that came from this guy go over here. So instead of taking the average of the coefficients, you keep all of them over here, and you actually take the average of the alphas. And I forgot to divide this by L. Does it make sense? So this is the multi-cut version of the SDDP algorithm. What are the main things over here? One opening, one cut. When you solve this problem, you generated a cut that goes right away over here, which is different from the previous case, so that in order to have one cut, you had to solve all the problems. What else? Cuts remain separate. So, yep, you don't take their average, you don't merge them. However, the main issue is that this optimization problem here is larger because it has more variables and more constraints than the other one. Again, we solve all the openings to generate all the cuts. The last comment that I want to make in this presentation is about more information on that thing that I mentioned, the stage-wise independent of the uncertainty. Okay? Like I mentioned, SDDP only works if your problem is stage-wise independent. Then the natural question is, well, most of the real problems are not stage-wise independent in terms of their uncertainty. For instance, the problem that I started mentioning to you, hydrothermal dispatch, is not stage-wise independent. Why? Because the inflow, the water that rains today, has a correlation with the water that fell yesterday. So the rain of today is correlated to the rain of yesterday. This is an empirical fact. You can just you can simply compute that and see that there is a non-zero correlation between these two variables. So this means that the problem is not stage-wise independent, and yet people found a way of handling that. And there are, well, two seems to be the important number over here, there are two main approaches to handle that. One that is called the autoregressive time series approach, and the other one, which is called the Markovian approach. The autoregressive approach first. So this will be our random variable at this point. This is the same single stage decomposed problem that we have, but this is an uncertain variable. But I'm saying, what if this uncertain variable is not stage-wise independent? One of the ways of handling that is representing, rewriting this random variable as an autoregressive process and hope that in this way you can have only stage-wise independent variables. So how do we do that? We expand the states because, well, before our only state was X. Now I added a new state Y. Y is slightly special. This notation is very common in SDDP, and this thing here means this vector, Y1 all the way to YT. So whenever you see a bracket thing like this in multi-stage stochastic programming, it means this vector over here, okay? So this means that I expanded my state space from only X to also contain this other Y variable over here. Y will be, YT will be the variable representing the current state, the current uncertainty. And YT is a decision variable, so it should be here as well. That depends on the past plus the source of uncertainty in this problem, which is this psi over here. And this psi, hopefully, will be stage-wise independent. So even if B is a stage-wise dependent process, maybe we can find a rewrite of that stochastic program saying that, yeah, a linear combination of past values plus a stage-wise independent random noise is equivalent to B. For simple correlation, this makes sense because if you wanted just to represent the correlation between the water today and the water yesterday, we could do that through this autoregressive process over here. And the other possibility is what people call the Markovian SDDP. So on the top here, the same problem, the same random variable that is stage-wise dependent. But here we span the state space with a Markov state. So this is not a decision variable. This is just one Markov state of a Markov chain rule. But then you're just saying that the randomness constrained to that state that you're at, for instance, MI, this thing is stage-wise independent. And then you have two possibilities of transition to the future. So you have two different future cost functions. One that depends on one Markov state and another one that depends on another Markov state. And there is a Markovian transition probability over here. So you have, in this case, you kind of have two possible futures that might happen. This is, in some sense, a bit more advanced, but I wanted for you guys to know about that so you have an idea when you read something on these terms. And because in many problems, this is actually fundamental if you want to model something correctly. And the last group of things that I wanted to talk to you about in just 2 more minutes is software for SDDP. There's a lot of open source software for doing SDDP. If you're already using Julia and Jump, like you briefly mentioned, this is kind of the best software from a friend of ours from New Zealand, Oscar Dawson. He wrote sddp.jl as a software that you can readily use. And there are other versions in Julia, other versions in MATLAB, and versions in Python, because yeah, people love Python, so why not show you that there's something over there as well. The Julia version of SDDP is very interesting. Just like we wrote our problem in terms of this stage representations of the problem, we can do that in SDDP. So SDDP lets you write what it calls a policy graph, so that you write for each stage the optimization problem that you have. You add the objective function for each stage separately, and then you define how the noises occur in this algorithm. So this is defining the possible noises at each stage. This SDDP model this SDDP software does not allow you to use automatically non-stage-wise independent randomness. If you want to do that, you either have to use the Markovian style or the autoregressive style. In the autoregressive style, you have to add additional variables over here, in particular, additional state variables. And in the Markovian style, you need a special policy graph that you can find in the docs. And with that, I will finish the presentation. I added here, you see when I send you some extra slides on risk aversion. I will not go into that because that's more advanced stuff, and I think we went already to a bunch of details. And there is a paper that I wrote about that, which is interesting if you want to work with risk aversion. But I would focus on the main material that was presented over here. So that's it, folks. I'm open for questions. I hope that you can take something out from this class. And I'm here right now for answering more questions. I will be available online for more questions. And we can even schedule with you some extra time so we can talk more details about this. I'm open for that if you need more time. So that's it.
Thank you very much, Joaquin. That was very nice and very thorough. This, I think, for me at least, was a very nice refresher, and I got to remember a lot of the stuff that you taught me in your classes in Brazil. So thank you, and I will throw to other people with an extra incentive that those that have not yet done anything online on the discussions, I will do a small quiz after you make your questions to Joaquin. So ask all the questions that you need to ask to make sure that you understand the contents that were delivered today. So this is the actual incentive that you have to ask your questions and make sure that you understand at least the main topics that he talked about today. And I've delivered questions for each one of you guys, given the topics that we will talk eventually in the future, so that you deliver a good topic at the end, connected to these things that we talked about today.
may not be directly related to what we're talking about today, but do you have any suggestions or ideas about how to frame it for, say, general non-convex or even mixed integer optimization problems? Because say, when we solve an ACOPF in power system, then you don't necessarily have these good cuts and bounds, right?
Yep. Yeah. So the problem that you're touching is related to something that I mentioned when I was talking about DDP. Actually, here. I said that convexity was the key requirement for this algorithm. And the main part that convexity appears is when we're doing the Bender's decomposition. Because if your future function is convex, you can always represent it by cutting planes perfectly, as long as you have enough cutting planes, right? However, if your future cost function is non-convex for some reason, like this, if you try to represent by cutting planes, you can do a lot. You can do like this, but then there will be these areas over here that you simply cannot represent. Because if you try to add a cutting plane to remove a solution over here, this cutting plane would cut other valid solutions, like this one, this one, this one. So this cutting generation scheme will not work out of the box for non-convex problems due to these reasons over here. Okay. However, there are a few things that you can do, and there are at least two of them. Okay. The first one is that just go live with that in the following sense. Instead of treating SDDP as a globally optimal algorithm for solving a problem, you can just say, yeah, I am aware that I will not be able to properly represent these regions of the problem, but whatever. Let me go with that. I will represent the future cost function the best way I can. So it will be this convex hull over here. And to do that, you can simply, when you have this forward and backward passes, you can simply have your nonlinear program in detail in the forward pass. So you follow interesting paths into the future, understanding all the nonlinearity of the problem. But when you do the backward pass, you solve a convex version of that problem. So you don't cut off valid solutions. So this combination of everything we talked during the presentation was, yeah, the forward pass and the backward pass are the same problem. They have to be solved as the same problem so you can converge the thing, so you can find the globally optimal solution. But if your problem is non-convex, yeah, the backward pass, use a convex version of that, but in the forward pass, use a detailed version of that. So you can get to kind of using this thing as a heuristic or some sort of reinforcement learning algorithm. This would be SDDP acting as a reinforcement learning algorithm. This is probably the better version for scaling. So if you want to solve a large version of a non-convex problem. On the other hand, if you want to assure global optimality, you can use the other thing that we briefly mentioned, which is SDDP. So stochastic dual dynamic integer programming. To do that, there will be a few modifications that will be needed in the algorithm. One of them is that your state variables will need to be binary if you want to use the standard SDDP algorithm. That makes the problem harder to solve. But that's actually flexible because you can represent continuous variables as binary expansions with integer variables. So you don't lose representation capability, but your problem becomes much harder to solve. And the other challenge is that when you're doing cutting planes, in SDDP, we use that fact that the dual variable is well defined and will help you define the derivative of the cost function. If you have integer variables, this thing won't be as easy to compute. You have to use something that people call Lagrangian cuts. Lagrangian cuts are a special type of cuts that you can compute out of mixed integer programs. The basic idea is that you find the solution of the mixed integer program exactly with a mixed integer programming solver. And then when you're computing in order to compute the jewels, which won't be available, you have to solve a Lagrangian relaxation of this problem over here. And that can give you even convergence. So if you use that SDDIP, in theory, you can find the global optimal solution. The issue is integer programming is much more complicated than linear programming, so the algorithm is much slower to converge. Okay.
Thank you.
Perfect. Joaquin, thank you very much. I think in order to have more time for you to answer questions, I think we'll leave the rest of them to offline, if that's okay with you.
Yeah, sure.
Thank you. It was very nice and a very thorough presentation. Let's thank again our speaker.
Thanks, everybody.
I will stop the recording right now, and I will thank you again.